Hi, and welcome again to my Physics Online video lecture series. Today's video I'm going to be talking a little bit about sound as a wave, and I'm going to be talking in particular about things like how is sound like and unlike the waves that we studied in earlier videos in this series. So in earlier videos in this series, basically, I discussed like a wave on a string, one-dimensional waves in general, etc. So how is sound like that, and how is sound not like that? And to set ourselves up for this discussion, I have an image that I've pulled from the Open Education resource, the textbook University Physics Volume 1 by OpenStax. And you can go access that textbook for free on the OpenStax website. Just search for OpenStax and then look for the physics text. There's an AP physics text, there's a college physics text, there's a university physics text in 3 volumes. This one's from Volume 1. So what is this image? Why did I put it here, and what is it showing, and what do I want to say about it? Well, this is basically kind of a visual representation of a sound wave produced by a speaker, and we're looking at kind of 2 aspects. One is, what is the pressure doing? And the other is, so where are the individual particles? And this already is a little bit different than what we discussed with, let's say, the wave on a string, right? When we did wave on a string, what we cared about was displacement from equilibrium for each basically like element or like section, if you will, like really small sections of the string. And so we represented that by y, and we could write something like y is equal to y max times the sine or the cosine, whichever you'd prefer. We'll do sine of k wave times x, x being position along the string, minus if it's traveling to the right, or plus if it's traveling to the left, omega t plus some initial phase. Okay, and so each part of the string, maybe you have a horizontally oriented string. Each part of that string is either deflected upward or downward. So we've chosen y to represent up and down, and x to represent location along our string. So coming back over here, these sound waves, you'll notice that we don't really seem to have a y, or there is kind of an x, but there's not really a y anywhere. So why is that? Well, neither of these things is really trying to describe that motion per se. It's still a wave, but you're no longer looking at horizontal, vertical deflections of a string. You're looking at deflections of, let's say, air molecules, if this sound wave is in the air somewhere. And there's sort of 3 things that you could look at. This is showing 2 of them. It actually is showing all 3, albeit 2 in the equation form and 2 with 1 duplicate in the picture form. Okay. This one right here, the picture is trying to convey pressure. These lines, essentially where they're more closely spaced, are meant to convey that this is a high pressure region, HP for high pressure, or it's a compression region. And then where they're less densely spaced, This is low pressure or rarefaction. Okay? So if I was just going to look at what is the pressure doing here, I would basically say that the change in pressure from background or equilibrium, remember that y was change in displacement or change in position, displacement from equilibrium position. Here, we're change in pressure from equilibrium pressure. Your equilibrium pressure might be something like 1 atmosphere. Your change in pressure might be something like even like a few pascals or less, to be honest. It's very audible to have a few pascals change in pressure from that background. You don't usually get a change in pressure of 1 atmosphere. You'd end up with wave breaking and some serious shock waves long before you hit that level of pressure. Okay, so the change in pressure is many orders of magnitude less than the equilibrium pressure, typically. But this change in pressure can be modeled by a sine wave. And there is, of course, some initial phase. And then the second way of representing it would be to look at these little dots kind of are supposed to represent particles or molecules of air, let's say, particles within the medium that your wave is traveling through. Sound wave doesn't have to just travel through air, by the way. It could travel through any medium as long as there's material to carry the wave. So this could be sound underwater. It could be like a sound wave in the earth during an earthquake. For that matter, it can travel along like a metal rod instead of a three-dimensional space. But in any case, these represent the molecules of the media that are carrying the wave. And what you'll notice is that you have some regions that are high density and some regions that are low density. And again, you have a background density in air under standard temperature pressure. Your equilibrium condition is about 1.29 kilograms per cubic meter. So this density, if you wanted to look at it in terms of mass density, it might be, for a very loud sound, it might be a gram or two per cubic meter change in pressure. So I'm trying to make that clear because these diagrams make it look as if there's regions where all the particles have gone away and where the pressure goes to 0. That's not what's happening at all. But more particles are missing from that region and are displaced to a different region. And that actually brings up the third way of describing it. So mathematically, the density, you know, we like to use rho for density in physics. Essentially, you're looking at a change in density, and that should be a change in density amplitude. Again, this might be like 1 or 2 grams per cubic meter for, you know, very, very audible sounds. Times the sine of kWx minus omega t or plus omega t, depending upon how you want to propagate this thing, plus phi. Okay. And then the last thing that's being shown here is the displacement. So this equation represents particle displacements. And essentially what you have to know here is that particles are displaced away from the low pressure and into the high pressure regions. So it's actually kind of true to say that this region right here, where you have a relatively low pressure, is one in which the particles have made a lot of displacement. So like this particle here may have come out of this region. This particle here may have come out of this region where it's lower pressure. And then the high pressure regions, you have relatively few particles that have been displaced from there. So this right here is actually a displacement from equilibrium equation. Now, you might want to know, why is it that we're using an S rather than a Y here? And the answer is this. With the string, so if I go back to my wave on my string, with the string, equilibrium might look like this. The string carrying a wave may look like this. Whoops, it's kind of a bad drawing of a wave, but maybe my string with the wave looks like this. Each point here is displaced vertically, so up or down. The wave is moving left and right. So this is transverse. This is what's called a transverse wave. Okay? That means, again, that the particle motion is perpendicular to the direction of the wave's propagation. So each element of the string is just moving up and down like this, but the wave is moving from my left to my right, or from my right to my left. In a sound wave, these particles, they displace more or less left and right in this picture, and at a moment later, a snapshot taken later in time, the particle will actually move back this way. Okay, so my particles are actually just moving back and forth like this. My wave starts at the speaker and moves away from the speaker. Okay. So these are what are called longitudinal waves, because the particle motion, the actual motion of the particles creating the wave, is parallel and anti-parallel to the direction in which the wave is propagating. All right. Another difference is that with the wave on a string, you have a 1D wave. So this is one-dimensional. With these longitudinal waves, the waves are not, they can be one-dimensional. You can have a wave on, say, a rod, and these pictures certainly make it look like a one-dimensional wave, but a typical sound wave in air is not a one-dimensional wave. When I'm speaking to you, the sound doesn't just travel this way straight to you or straight to my microphone. It actually travels in all these directions away from my mouth. It's 3 dimensions. There's an X, a Y, and a Z component, let's say. And so for that reason, although we use X still to represent the position that you're looking at, properly speaking, this is actually a wave vector, this is actually a dot product, and this is a 3-dimensional XYZ vector in space. Okay? Now, when we're talking about density and when we're talking about pressure, there's no real confusion as to what X would represent versus what P would represent. But with displacement, we no longer can just simply use Y as our displacement term and X as our distance term if we want to use X, Y, Z to represent coordinates. Okay, and so that's the other big difference. That's all that I have time to make today, so Farewell.